welcome back to another episode of the Python People podcast, the home for global technology leaders to share insights with the tech community. And this week, we are honoured to be joined by our special guest, Matthew Lee. Matt, thank you for joining us today. How are you doing?
I'm very well, thank you. Thank you for having me.
You're more than welcome. You're more than welcome. I'm looking forward to our chat. So, Matt, to introduce you to anyone that hasn't had the pleasure so far, you are the principal data scientist for Sonrai Analytics, and Sonrai, a business doing some very interesting and pioneering data-focused work in the biomedical space. And I'm sure we'll get into talking about that in a wee while. But I like to start where I usually like to start, which is to talk about you and your background as a leader in data. So yeah, it'd be great if you'd be so kind to give us a little bit of your journey through data so far, and a bit about your background and career to date.
Sure. So I guess a good place to start would be at my degree. So I did a physics degree at York, and from there I joined the NHS on a clinical scientist training program. So that was training up to become a medical physicist within the NHS. That was really interesting. So it was a 4-year scheme, and part of it was going to UCL, University College London, to do a master's in, I think the title was radiation physics, but it was a medical physics degree.
Yep.
So that was very interesting. Started to get, I had a bit of an introduction to coding when I was doing my physics degree, Fortran and things like that. So I'm showing my age a little bit. Yeah. But then in the masters, I got introduced to MATLAB and started using that in little projects as part of the training scheme. So it was a bit of nuclear medicine, radiation protection, and medical imaging, which is what I've ended up in. But for a long time, I was more specialised in nuclear medicine, which was very interesting. And did a master's project in that field, which was cool. It was actually using Java for that project, just because my supervisors were well versed in Java, and that's where I could get the help.
Mm-hmm.
So that was really cool. I also did a bit of lecturing when I was there. So that's the only time I've done lecturing, but that was a really interesting, enjoyable experience. So I've done this training scheme. I was based in Canterbury at first, but it took me to Brighton and then to Belfast, that's where I'm based now.
Mm-hmm.
So I was still in my medical physics role in Belfast. And at that point, I was working more in mammography physics, so the testing of the equipment that kind of provides the images for the screening program. As within breast screening, at that time, you were starting to hear in research papers about AI starting to come in and assist radiologists in, so there'll be something called CAD, computer aided detection. I know that's an acronym. That acronym means something else in a different field, but computer aided detection is where AI first started coming in. And that was quite interesting. So in my role as a physicist, I would kind of read around these things, but not actually get to apply them. So yeah, that takes me up to getting into Belfast. From there, I left the NHS and joined a company that supplied imaging equipment to the NHS. So that was an interesting role. I'm kind of going off the data subject here because it had not much to do with data. There was training users, radiographers, and sometimes radiologists on new bits of kit, installing the kit, doing kind of quality control thereafter. It was an interesting and varied job. It also involved a lot of travel. So when my family began to grow, I decided to go back to what I was more interested in, which was doing the coding. And I got a job at an insurance company of all places. So Allstate Insurance in Northern Ireland had this kind of incubation program for machine learning engineers. They were aware that there's well, especially at the time, there was a lot more demand than there were machine learning engineers. So they had this really well, it was a great program to train people on the job, people that have come from maybe a scientific background with a bit of coding experience. So that's fantastic. And I was working on images there as well. So one of the main projects I was doing working on was trying to automatically read VIN. So VIN is the vehicle identification number, not the big license plate, which is fairly easy to read. The customers have taken pictures of the VIN in their windshield, a long 17-digit alphanumeric, sending it in, and so this was being read by a person generally, and taking a lot of time, prone to kind of keystroke errors, entering 17 digits when it's not like a word, it's just a random alphanumeric sequence. So working on automating that, which was really interesting. Use one of the tools or algorithms I stumbled across to actually implement that and execute it was called UNet, which is a really popular model in the kind of, well, it was designed for biomedical imaging. So when I was researching solutions for that VIN problem, I came across this, and then I went down the rabbit hole, could see how these algorithms are helping back in the kind of healthcare role. So like I say, I was in the NHS for nearly 10 years. I had a passion for that kind of healthcare role of the feel-good factor at the end of the week when you know you've helped people. So that got me interested in applying the skills I'd learned at Allstate back into the healthcare kind of domain. And then a job at Sonrai Analytics came up. So Sonrai is the Irish word for data. It's an Irish company. Data analytics. I was approached about this job where they were saying, apply all of these things back into the healthcare role, work with really interesting data, really cool companies as well in partnership. I joined in April 2020, so right at the beginning of the pandemic. It's getting a bit of grief because it's a startup. So my partner was saying, do you want to join a startup at the beginning of the pandemic? And everyone's worried about a recession. So a bit of a jump, but I really liked the team, and it's worked out really well. So I joined as a senior data scientist, then since been promoted to principal data scientist. So it's Sonrai. So I'm rambling. Stop me if I'm rambling.
Yeah, it's good to know.
So Sonrai, I'm mostly working back in the imaging space again. So particularly with pathology images. So pathology images are they're really interesting to work with. They're vast. That's the main main difference about them. So in many ways, it's similar to other images you get in healthcare, like CT, MRI. Some of them are kind of DICOM compliant, same as those. The difference really is the size of the images. So they're almost always gigapixel, so billions of pixels in a single image, and the resolution. So you get resolution down to about 0.25 microns is the industry kind of standard for the resolution of these images. So that's how you get such a large image, because each pixel represents a really small area. And that presents particular challenges for applying these algorithms. So you can't feed a gigapixel image into a neural network. It just doesn't. There's no unless you've got access to a supercomputer, you just don't have the capacity to load that into RAM at once. So it presents interesting challenges, which are fairly unique. There are other domains which similar problems, like geospatial data, for instance, just because of the scale.
Scale, yeah. But so, what sort of challenges do you encounter with those types of images that you say you don't necessarily find in the not quite as vast images?
It's kind of an engineering problem, really. As it was partly engineering, and also if you take some of the popular machine learning challenges that have kind of helped machine learning progress, specifically computer vision, like ImageNet. So ImageNet is I don't know how many images there are, but the pictures of cats, dogs, and etc. But they're typically like a couple of hundred pixels square.
Yeah.
And you can put those on through a neural network. So you have an input tensor, which is a couple of hundred pixels square. They typically get reshaped to like 256 by 256 or what have you. And you could do that with a morphology image. You could resize and interpolate to get like a thumbnail, but then you lose all detail. So there's a reason they're scanned at such high resolution, and that's because if you want to see cells and the detail around the features of tissue, then you need to have that resolution. And if you want to have that resolution and capture any kind of area of significance at all, then you end up with these very large images.
I see.
Yeah. So the challenge is in how you use deep learning. You apply deep learning to these very large images, which are interesting, and there's different solutions to that. So multiple instance learning is a really cool solution, and then there's kind of just break it down into chunks. So tiling is the kind of what we would say in the industry. So you tile an image, you break it down into 256 squares or 128 squares, and apply deep learning at kind of that tile level, and then aggregate the results thereafter. So that's and there's more solutions as well, but they're the kind of the main ones there. So.
Cool, great stuff. Yeah, well, it's always really, never having done this job for as long as I have, I never get tired of hearing people's journey into data science, because one of the things I love about it is there's no kind of clear path necessarily, or a classic way into data science. I guess you could go to university and study data science and analytics or whatever, and then maybe go into that. But generally speaking, you do tend to find that people, I guess because it's still a relatively new area of technology in terms of how it's labeled now. A lot of people kind of find their way into it, and you tend to see it attract a lot of people that are very bright, very curious, sort of problem solving type professionals that sort of understand the value that data science can bear upon solving really, really complex problems, and then sort of go into that field, and like I say, find it very rewarding. And I think we've definitely seen since the pandemic, personally, I've seen a big shift, I think, in people's conscious towards picking companies where, one of the great things about data science, obviously, is you can solve problems in all, it's been applied in all walks of life, all different domains and sectors, but definitely seen a big shift towards people trying to solve problems in industries where they are making a difference, like I said, and can go home at the end of the day with a smile on their face, knowing they've actually had, made a difference. And how much does that factor into, to you? Could you see yourself doing data science in a different domain, in a different industry, or do you feel that sort of impact of what you're doing in the healthcare and sort of biomedical space is?
That's an interesting question, because there are obviously, like you say, a broad range of industries where data science has been applied.
Yeah.
In particular, I'm sure the salaries in finance are pretty eye-watering. In fact, you see salaries pop up and it does it does turn your head sometimes, but yeah, I really get a lot of value from knowing what I'm doing is benefiting people in such a direct way. I don't mean to discredit or jump on people doing it in finance or whatever is grand, but for me, I do value that kind of direct effect of what I'm doing, if you like. And there's other areas which I would consider working in the future. I could see what I'm kind of applications of what I'm doing being used in things like recycling or green tech, if you like, eco tech. Recycling in particular is yeah, computer vision is really handy for automating things which are fairly mundane. So if you have a kind of recycling conveyor belt and you can pick out plastics and metal and things like that, I could see that the skills I've got from doing this role and previous roles could be useful in something like that.
Nice.
So and other areas as well. That's just one example.
Yeah, nice that you can sort of see a transferability, but it's still within a domain that's kind of focused on tech for good as well, isn't it? And that would have a social impact. So yeah, it'd be a bit of a shame if you could yes see that it maybe had transferability to the tobacco industry or something. So it's good to know you can keep it within a social impact space. But no, I mean I am we are, I guess, as a business we are quite sector agnostic, very much focused on the data and tech vertical, but we deal with clients across a range of different sectors. We do, by virtue, I think, of our kind of mission and our ethos as a business, we do actually end up working, partnering with a lot of tech for good businesses. And one of the areas that I'm always really passionate or really interested in, I guess, actually, is the kind of, the health tech and the biomedical space, because of the, like I say, you can see the direct impact on actually what you're building, how that's genuinely helping to save lives. And I just think it's so interesting in terms of, like I said, how computer vision is sort of really evolving to bring an extra layer of kind of sophistication to what we do. But from your experience and your kind of expertise in the domain, what other applications, I guess, of machine learning or data science are you most excited about in the world of biotech?
So yeah, staying on computer vision for a sec. So I mentioned in the intro there, computer-aided detection for mammography. So I can see that principle being applied to all sorts of images for all sorts of so screening programs in particular. One of the things with one of the problems with screening programs is by definition you're applying them to vast swathes of the population. So you've got this large burden then on generally very well paid and very well trained people. So it could be a radiologist or a pathologist or something else to analyze these images. And I think both in pathology and radiology, I think the average age is very high, and there's concerns of having enough people in the future, enough skilled people to read these images. So where you've got that scale problem, obviously when you've trained a model, it doesn't get tired. You can deploy it anywhere, and you can run through images. You can scale to kind of however many you need. So having that is really valuable, and you can utilize that in a number of ways. You can have it as computer-aided detection, so you take a bit of the burden off radiologists, say, for example, because you're showing them areas of concern that they might want to consider in more detail. So it's a tool, or you could say, let's take because with screening, the vast majority are negative, and you can say with a model, you get an output which sometimes would be confidently negative, and sometimes kind of indeterminate, and sometimes confidently positive. So if you could take the confidently negative and say you don't need to worry about these ones, we're really sure that there's no pathology here, and that can really reduce the burden as well, and let the human experts focus on the things where the model struggles. So that's one area. Another area I think is where it's really hard to combine information from different sources. So say you've got imaging data, so it could be pathology or radiology, like I say, and genetic data. You've got those two data sources, and you've got the ground truth for what you're trying to predict. So it could be cancer or cancer stage, for example. So if you combine those two in a kind of conventional way, then it'll be the output of the imaging and the output of whatever the tests. So it'll be kind of two solo figures that get combined to predict something else. What you can do is say have the features from the imaging. So rather than go right to the end and say this is a positive kind of case for the imaging test, this is a positive case for the genetic test, you can take a step back and take some of the calculated features from both of them and combine them. So in our field, it's called multiomics. So multiomics kind of analysis.
Okay.
Yeah, that's really interesting, and that's something that is very hard for a person to do. You can feed that information into a model, and it can learn some really cool stuff. It might learn that such and such gene with such and such feature from an image is a really prognostic factor. That's something that'd be very hard to teach someone, or hard to learn. And I'm convinced that multiomic kind of strategies will identify these new kind of combinations of features. Well, in fact, it already is proving really effective by combining like models with on tabular data and imaging data, for example. It's already proving really effective at prognosis.
Brilliant, yeah, fantastic. That's great to hear. It's already having a big impact. And you mentioned earlier kind of the size of the images that you're working on. You sort of see a little bit of crossover with the likes of kind of geographical data in terms of sort of volumes. Like, are there any other areas where the kind of work you're doing, you're seeing any interesting crossovers with other industries in terms of its application?
So geospatial will be the main one for the imaging in terms of the kind of scale is fairly unique. There's astronomical data as well. There's that kind of scale, but that's geospatial, just pointing in the other direction, right? Back down to us. So yeah, for vision, that's the kind of main parallels, if you like, for the pathology work. But then for computer vision in general, there's applications everywhere. So we generally we use transfer learning. So we take the pre-trained weights from the likes of ImageNet, and it still kind of boosts the model's performance. So models and architectures that are being developed for general use are getting kind of brought into the medical domain and being applied to all sorts of images, medical images, including histopathology, which is very focused. So,
cool,
yeah.
Interesting stuff. And you've obviously come from this kind of physicist kind of physics background, physician background, and kind of moved into the world of data. Do you feel your background prior to getting into data science has, I guess, domain knowledge aside, do you feel did you sort of pick up quite important traits that you think have helped you in your role? And I suppose, what do you feel are the most important traits as to be a quality data scientist in your field?
For sure. In physics, I think the kind of problem solving aspect of physics, both in the lab work from going way back to my undergrad. That's really important. It's the skills that you learn from that process. Doing labs and trying to figure things out from the data that's presented that you obtain when you're doing the lab work. So there's that kind of the mathematics that underlies physics is the same mathematics that underlies data science. So a heck of a lot of calculus in physics, and calculus kind of underlies the statistical learning that we all deploy every day. So that was that's a big help as well, and in statistics in general. So especially with the medical physics degree, there's a module on statistics, and that was really valuable. Still look back at the notes every now and then, and having that kind of information and that grounding to then critically analyze papers. So doing research is key part of the job. You want to stay on the cutting edge or close to it, and being able to analyze papers and from that kind of point of view is something that I really picked up both in physics and medical physics, perhaps even more so. But yeah, the problem solving, mathematical kind of background, and then stats, because it's all statistical learning really.
Yes. Yeah, I guess that's a very good point. A couple of things quite interesting there. I guess like the ability to analyze and understand papers, definitely, I suppose, very key, isn't it? Especially in the sort of the biomedical world, of taking learnings from a paper and understanding how you can transpose that to your situation or your particular problem. Yeah, absolutely. And
The the engineering side shouldn't be overlooked. So if you sometimes academics will come straight from their kind of academic field, and I did this, I must admit. So coming from the NHS into Allstate, I think my coding was okay as an individual, but that's not how you work when you join a company that writes code. So when you coming from the academic world, you might be quite good at programming, but programming is also a team game, and you need to make sure your code is legible by everyone else. So that was a bit of a shock for me. Maybe not a shock, but a learning curve, making my code deployable, shareable, and understandable, maintainable.
yeah.
So yeah, that's another key thing that is kind of learned on raw as well.
Yeah, I think it's a very good point, because again, a lot of people say, well, data scientist is this kind of newfangled, sexy term that flies about in businesses now, but actually, like I say, a lot of it at its heart is statistics that has been around since math draws off maths and statistics, which obviously in the commercial world have been used and applied well for donkey's years. But I think the key differentiator, like you say, or kind of where data science really sort of comes into its own, certainly with kind of applied data science now, and like I said, when we're kind of building out products and things like that, it is that coding piece, isn't it? It's not necessarily just being able to hack something together or build a model or put something together in Python. It's actually about building best practice, like you say, scalable, deployable code that and I think that's often the piece that a lot of people do struggle with, because it's and you could be the brightest, most academic person in the world, but unless you've actually you've been around computer programming for long enough that you understand best practice software engineering principles, it's quite a difficult thing to pick up, isn't it? But those data scientists that can, I guess it's a bit of a Venn diagram, isn't it? I think there's that famous famous diagram out there, which is mathematical and statistical skills, it's domain knowledge and sort of soft skills, and then it's also computer programming, and that's the kind of the data science, that sweet spot that sits in the middle. But no, I definitely would agree with that. Okay, fantastic. Well, I think it's been a really, really interesting chat, Matt, and very much enjoyed hearing your perspective on on the great work you're doing, and kind of how data science is being applied in really innovative ways to the biomedical space. And I like to sort of draw a close to every podcast I do by asking the same question at the end, which is how I guess what is your favorite piece of advice that you've ever received? If there's something you could pass on to your fellow human, what would your favorite bit of advice be?
It's a tricky one. Well, there was a lecturer in my undergrad who it's kind of a key principle in physics, but he really hammered it home. So break down any challenge into first principles, and that's a key thing to do in physics. You understand the first principles and build them up, build on top of that. You come to the answer. That applies to coding as well in a way. It's kind of if the single responsibility principle for a function, and it's kind of a similar analogous principle, and it's done me well. So subjects or problems that can seem quite daunting at first when you break them down like that, the answer comes out. So,
Yeah, I think that's a nice kind of analogy to apply to all types of situations in life, isn't it? Not necessarily just data science problems or physics problems, but actually, any problem in life. Like say something that's quite daunting, actually work out. Rather than looking at it from a glass half empty point of view, look at it as a glass half full point of view of what's the first most actionable step, and how can we break this problem down into the first sort of mini chunk, and go forward from there. So yeah, I think that's a very, very good bit of advice to for us to end on. So perfect. All right. Well, again, really enjoyed the chat. Thank you very much for being with us today and sharing your wisdom. And look forward to hearing more from Sonrai Analytics as time goes on, and I'll certainly be keeping up to speed with the great revelations and advances you guys are making in the world of healthcare.
no, thanks very much. Appreciate the time, and I've enjoyed it. Thank you.
Good stuff. Bye for now.